Hello everyone and welcome to Quantum Bits, Bytes and Insights. I'm Sissel, a quantum photonics engineer at Sparrow Quantum, and I'll be your moderator for today's Lunch and Learn session. Today we are diving into the latest academic advancements in entanglement sources coming straight from the Niels Bohr Institute. Sparrow Quantum started as a spin-out from NBI, and we're still closely connected with the research group there. We're super excited to highlight their work today. We'll kick things off with a brief talk by Jan Heiden, who will introduce the paper, Deterministic Photon Source of Genuine 3-Qubit Entanglement. After that, Jan will join me along with one of the authors, Ming Lai, for a live Q&A session. So have your questions ready and submit it in the Q&A box during the talk. All right, let's get started. Over to you, Jan.
Very much for the nice introduction, Sissel. My name is Jan. I'm currently an industrial PhD student here at the Niels Bohr Institute in association with Sparrow. And today we're going to have a look at some of the more recent research being conducted here at NBI. And the topic of today's talk is going to be on deterministic entanglement sources. Now, before we dive right into what that actually means and how to build such a source, we're going to have a look at why these sources play such a central role in this entire field of quantum computing and quantum communication. So, as most of you might know, there's a lot of different platforms around on which you can build a quantum computer. One of the most prominent examples might be the superconducting qubits. This is an approach, for example, followed by Google or IBM. But there's many others. There's trapped ions, there's defect centers either in diamond or in silicon, and among some other approaches, last but not least, there's photonic-based quantum computing. Now, on all of these platforms, you can build qubits, and they're all going to have their advantages and shortcomings. But there's one thing that is very unique about this entire idea of using photons as qubits. So, first of all, photons tend to interact very weakly with their environment, and that's a very good thing, because that means that external perturbations will not hurt our system as much. However, the key thing about photons is they are not static particles, right? So they're literally moving at the speed of light. And that makes them the natural choice for all kinds of communication. And just in the way that we're currently using photons for the communication between classical computers, ergo the internet, they are also the natural choice for communication between quantum computers. So the quantum internet. And the key message here is that regardless of which of these platforms we're eventually going to be using for the quantum computing itself, whether it's going to be a photonic-based quantum computer or one or the others, we're always going to rely on photonic-based qubits for the communication between the computers. Now, the deterministic generation of entangled photons is a key requirement both for photonic-based quantum computing and for the communication. That being said, let's have a look at how to build such a source. Now, for those of you who've watched the last episode of this series, this structure might seem familiar. What you can see here is a photonic crystal waveguide that is linked to a grating coupler in the upper right corner that will be used to couple light in and out of the system. Now, here in the center of our waveguide, we have a quantum dot, which is basically just a bunch of atoms. And we can use a red laser in order to excite this quantum dot. And then it will deterministically generate one single photon. And so this is a very, very efficient process with over 96% efficiency. And this photon is then traveling through the waveguide and can eventually be picked up by the grating coupler. Now, this is a very nice technology on its own, and it has a lot of real-world applications right now. However, the researchers here at NBI have taken this a whole step further by using this very same platform to generate entangled states of photons. Now, as already said, this talk is going to be based on this very nice paper by Yizhen Meng and Ming Lai Chen. For those of you who are interested in the topic, I definitely recommend reading it. It has recently been uploaded to arXiv and will be soon published in Nature Communications. So I definitely recommend reading it. You can find it either using the link or the QR code. And what the authors did in this paper is they used the spin of the quantum dot as an entangler between the photons. So they entangled the photons to the spin of the quantum dot, and then by actively controlling the spin, they created these larger states of entangled photons. But we're going to have a look at that in some more detail in the next animation. So as you can see, we're using the very same platform as before, only now for illustrational purposes we've added the quantum dot alongside with its spin. Now, before we start the actual protocol, we're going to do some state preparation. So we're basically initializing our quantum dot spin in a state of superposition. This is now indicated by the golden and the red arrow. Now, to start the protocol, again, we're going to use a red laser in order to excite the quantum dot, which is followed by the subsequent emission of one photon. Now, this photon is going to be entangled to the spin state of our quantum dot. And now, before we excite the quantum dot again, what we can do is we can actively flip the spin by using another laser pulse. Now, what that does is if we now excite the quantum dot again and emit another photon, this newly generated photon will be entangled to the new spin state of our quantum dot. And by repeating this process multiple times over and over again, we can generate these larger strings of entangled photons. And I really want to emphasize this here. So in the paper, for the first time ever using a quantum dot source, the authors have been able to generate genuine 3-qubit entanglement. So this 3-qubit entanglement consisting of 1 spin qubit and 2 photonic qubits. And this is really, really, really amazing because it's a proof of concept for scalable deterministic generation of entangled photon states, which, as you've seen previously, is a key enabling technique for the quantum computing and quantum communication based on photons. So that being said, as it always is in quantum world, it's not quite as easy as it looks from this animation. So we're always going to have a lot of contributions to our system which we have to control. And therefore also the authors performed a very detailed error analysis in order to better understand the fundamental mechanisms behind the system. Now, I do not want to go into any details of that here, just want to mention 2 examples of such contributions. So for the first one, we're operating in a solid state system, right? So we're naturally always going to have lattice vibrations, so-called phonons, and they can lead to phononic dephasing of our spin. Now, this problem, thankfully, is quite easy to manage by just going to lower temperatures. So if we're operating around 4 to 6 Kelvin, the phonons will simply freeze out. Now, the next contribution is not quite as easy to handle. So the thing is, the spin of our quantum dot will couple to the nuclear spin environment around it. And the problem with this spin environment is that it's fluctuating. So we'll introduce a statistical error into our system, which of course we do not want. But there's a clever solution to that. So by actively controlling the spin in a clever way, the authors were actually able to use this coupling in order to align the spins of our nuclear spin environment and therefore to stabilize it. This process is known as nuclear spin narrowing. So to summarize, we've seen how this very same platform can be used to generate strings of entangled photons in a deterministic way, and that the authors have performed a proof of principle by generating a genuine 3-qubit state of entanglement. Now, to wrap this up, I want to be showing you one example of how these entanglement states can be used for quantum communication. So let's say Alice wants to send a message to Bob. Now, this might work a couple of times, but we're naturally always going to have some signal loss. Now, the classical approach to this problem is to just generate a lot of copies of our signal and send all of them. So eventually one of them is going to reach its destination. The problem is that does not work in quantum world. So there's a thing called the no cloning theorem, which basically just states that you cannot make any copies of quantum states. However, there's a clever solution to overcome this problem as well, and this is known as a quantum repeater. So what the quantum repeater does is, instead of copying the signal, it will extract the information from it and re-encode it into a new signal that will eventually be sent to the receiver. However, this requires larger states of entangled photons. And the good thing about these larger states, these larger tree states, is that the information is spread out across the photons. So if we send our signal and we're naturally going to have some signal loss across the way, this does not compromise the information stored in the state. And the quantum repeater can then extract the information by performing some clever measurements and eventually re-encode the information into a new tree state. And this tree state can then be sent to the receiver. Now, I hope this makes clear how big the impact of this proof of concept is and how deterministic sources of entangled photons will be a key enabling technology both for quantum computing and quantum communication. So I'm going to join you, Sissel, now in a minute for the Q&A session alongside with one of the authors, Minglai Chen. See you in a minute.
Welcome back, Jan, and thanks for a great talk.
Thank you very much.
We're so fortunate to have Minglai here, one of the authors of the paper. And Minglai, you're a postdoc here at NPI as well?
Yes, I am. Thanks for inviting me, Sissel. It's great to be here.
It's great to have you both. We can start off with the first question, and please add all your questions in the box below. So the first question here, maybe for you as an author here, what fascinates you about this work, and what would you say is the key impact of it?
Right. So what fascinates me about the work is that we have now a prototype of a deterministic entanglement source, and a source can produce a 3-qubit entangled state. We call it GHZ states. These GHZ states are highly sought after by the research community because it is a fundamental building block for error and loss correction for quantum computing and also communication. As for the key impacts, I think there are two. The first impact is that we are now able to generate for the first time 3-qubit entanglement using a solid state source. And the second impact is that now that we have understand all the physical error processes that sort of limits the entanglement fidelity of the source, we are able to lay out a realistic and engineering path to further optimize the source and try to scale it up from here.
That is super exciting.
Yes.
Let's dive into the next questions. I can see there's more. So how do the quantum dots compare to other photon sources?
Well, I mean, generally, if comparing to a general photon source, first of all, our system is deterministic, right? So we can create these photons or these larger entangled states of photons in a deterministic way on demand. So this is, first of all, a big advantage in terms of scalability later on, and also, of course, efficiency, because we're not involving any probabilistic processes. But then still, even compared to other deterministic sources, these 3-5 semiconductor quantum dots have some advantages because, for example, they offer a direct bandgap, which makes them very fast and also very efficient. And yeah, so the last point I might want to mention is you can embed them into a circuit directly on chip, which is also a big advantage in terms of scalability.
That is cool. So let's dive into the next here. Why do we need entangled photons for a quantum computer?
Yeah, mainly because I mean it's basically the same reason that we showed in the talk as for the quantum communication part. So it's all about error management. If you build a quantum computer, you're naturally going to have some errors that will accumulate during the computation, and you have to deal with that. And the idea here is just the same. You're gonna distribute or encode this information in redundancy through entanglement of multiple photons.
Yeah, entanglement is the secret sauce of quantum.
Yeah.
I like that one. Yeah. And why do you believe that photonics will be the future?
Yeah, I mean, I guess there's many reasons for that. Also, the one we showed in the talk. But generally, I mean, photons are interacting weakly, so we have very good lifetimes for them. And also in comparison maybe to other qubit platforms, they are quite easy and quite cheap to produce, right? So
Yeah, maybe one more thing to add to that is that photonics is really modular in the sense that once we are able to get these single photon sources or entanglement source working with sufficiently high quality and efficiency, we can really scale it up to like a larger scale. So let's say, for example, if you have a working entanglement source, what you can do is you can implement multiple switches to do interleaving so that you can use only one quantum emitter and try to generate many copies of the same states, and then you can sort of direct all these states to like an integrated circuit, which you can make or manufacture in large scale by CMOS technology. And scalability in this regard is not really an issue.
That is really a nice advantage of photons.
Yes.
Yeah, it is. So there's one more here. Based on your initial insights, what are the main obstacles to achieve a scalable product, as you talked about before?
Yeah, as I have mentioned, there are two obstacles. One is obviously the quality of the source. So in the sense that we're talking about entanglement fidelity of the source. The other obstacle obviously will be the loss. So it's how much light you can couple out of the device, and how much loss you can sort of tolerate when you do all this quantum computing stuff. And yeah, so we already have several approaches to try to solve all these obstacles. But yeah, for example, let's say for loss, we already have something called active switching of the photonic readout basis. So in the current scheme that you see in the paper, we are doing all the readouts passively, in the sense that when you have a photon and you want to read out in like an X basis, then with the interferometer that we have, you can only do it passively. So 50% of the time, it will end up in the basis that you want, but 50% it will go to set basis, for example. And with active switching, the point is you can 100% direct 100% of these photons into the basis that you want. And so eventually you have an efficiency boost of factor 2 per photon.
and I guess that's also a major part of this paper, right? So that you've cleared out this roadmap in order to address the different issues that are currently there and understood the physical properties behind them.
Yeah, it's really a nice proof of concept. Yeah, super cool experiment. Yeah, so we can give a few more, yeah, a little bit more time for more questions to come in. And please just add them in the box below. And I can tell if you sit after this session and you have a burning question, then you can always email us on info@sparrowquantum.com with your question, and we will get back to you. Yeah, so it seems like we're rounding off here, but before rounding off, I would like to ask about this exciting work. What is next?
Yeah, so yes, there are two directions for next steps. Okay, first of all, the obvious next step is to scale this up a little further, to try to extend the number of entangled photons by 1 or 2. Then it ends up with a 4-qubit entanglement where you have 3 entangled photons with spin. And to do that, basically we have, as I've said, we have two directions. One is to improve the loss of the system by doing this active switching, for example. And we can also, let's say, switch to a one-sided waveguide, because at the moment we're using two-sided. So every time the photon is being coupled out of the waveguide, you lose 50% of the time. So in the next generation device, we are going to use one-sided device. So that's the first thing. The second direction would be to improve the fidelity. So from the paper, we have sort of understand that most of the errors come from two directions. One is the nuclear spin noises, and the other direction comes from the off-resonant excitation. So 11% of the error comes from the fact that we are exciting the wrong transition when we do optical excitation. So there is an easy solution to that for the next generation device, is that we will try to basically rotate the waveguide by 90 degrees. So it means that when you look at selection rules, that means that the outer transitions are being cycling. So whenever you do an optical excitation with a laser that has a bandwidth of 12 gigahertz, then all the optical transitions are sort of spectrally separated. So you are not addressing the other ones, but you're only exciting one. So it gives you a very pure photon without doing any effective spin phasing. So that is obviously the next thing to do.
So nice.
Yes.
Thank you so much, both
Thank you very
Jan
much.
and
Yeah.
Minglai, for sharing this amazing work from the S4 Institute. And thank you everybody for joining during your lunch break, using your time with us. And stay tuned for more quantum bits, bytes, and insights coming in the future. Thank you and bye.
Bye.